Welcome to this video presentation on conduction heat transfer. Today we'll be examining example 2, which involves calculating heat flow through a composite furnace wall. Let's look at the problem. We need to calculate the rate of heat flow per square meter through a furnace wall. This wall is constructed with 3 layers: an inner layer of 20 millimeters thick chrome brick, a central layer of 100 millimeters of kaolin brick, and an outer layer of 100 millimeter thick masonry brick. We're given a unit surface conductance at the inner surface of 74 watts per square meter degree Celsius, and the outer surface temperature is 70 degrees Celsius. The temperature of the gases inside the furnace is 1670 degrees Celsius. Additionally, we need to determine the temperatures at the inner and outer surfaces of the central layer. Thermal conductivities for each type of brick are provided, and we will assume a steady heat flow for this problem. Now let's begin with the solution by outlining the given parameters and setting up our problem. We have, as shown, the thicknesses of each layer, the thermal conductivities given for the materials, the unit surface conductance for each of the materials is also provided, as shown. First, let's calculate the rate of heat flow per square meter, denoted as Q. For a composite wall with convection at one surface, the formula for Q is the overall temperature difference divided by the sum of all thermal resistances. This includes the convective resistance at the inner surface and the conductive resistances of each brick layer. Substituting our known values and performing this calculation, we find that the rate of heat flow Q to be approximately 938.58 watts per square meter. Next, we need to find the temperatures at the interfaces, specifically T1, T2, and T3. Now, we can use the principle that the heat flow Q is constant through each section of the wall. So Q is equal to the temperature difference across the section divided by its corresponding thermal resistance. So when you start with the T1 and rearranging this, we find that T1 is equals to 1657.3 degrees Celsius. Now let's find T2 in a similar fashion using the same principle, and rearranging and solving, we find that T2 is equals to 1507.1 degrees Celsius. Finally, for T3, the temperature at the interface between the kaolin brick and the masonry brick, rearranging and solving, we find that T3 is equals to 238.7 degrees Celsius. So the temperatures prevailing at the inner and outer surfaces of the central layer, which are the kaolin brick, are as worked out, and this concludes our solution for example 2. Thanks for watching. Like, subscribe, and share.